If you close your eyes and picture energy, you likely imagine some kind of glowing blue fluid. You might see a crackling lightning bolt or a shimmering aura flowing from a battery into a light bulb. You perceive it as a substance. You think of it as a blob of something that physically moves from place to place. I must destroy this magic trick immediately, because that image is completely wrong. In the world of physics today, we have zero knowledge of what energy actually is. We do not have a picture that energy comes in little blobs of a definite amount. It is not a fluid and it is not a gas. It is not a ghost living inside the machine. It is a number. That is the entire truth. It is a mathematical quantity. It is an abstract bookkeeping rule that nature decides to obey for reasons we do not fully understand. Here is the reality of the situation. There is a fact or a law governing all natural phenomena known to date. There is no known exception to this law. We call it the conservation of energy. It states that there is a certain numerical quantity, which we call energy, that does not change in the manifold changes that nature undergoes. This is an extremely abstract idea because it is a mathematical principle rather than a physical description. It says that there is a numerical quantity which does not change when something happens. It is not a description of a mechanism or anything concrete like a gear or a pulley. It is just a strange fact that we can calculate some number, and when we finish watching nature go through her tricks and calculate the number again, it is exactly the same. Think of a bishop on a chessboard. If you look at the red squares, the bishop is always on a red square. You can move it, and you can dance it around, and you can distract it. But if you count the number of bishops on red squares, that number is conserved. Energy is like that. It is a rule of the game and not a piece on the board. To understand this, we have to stop thinking like physicists. We must start thinking like a mother dealing with a very mischievous child. Imagine a child named Dennis. Dennis has a set of blocks. These blocks are absolutely indestructible and cannot be divided into pieces. Each block is exactly the same as the other. Let us suppose that he has 28 blocks. His mother puts him with his 28 blocks into a room at the beginning of the day. At the end of the day, she counts the blocks very carefully. She discovers a phenomenal law. No matter what he does with the blocks, there are always 28 remaining. This continues for a number of days until one day there are only 27 blocks. Does she assume the law of conservation of blocks is broken? No, she investigates. A little looking around shows that there is one block hidden under the rug. She must look everywhere to be sure that the number of blocks has not changed. One day, however, the number appears to change again. There are only 26 blocks visible. Careful investigation indicates that the window was open. Upon looking outside, the other 2 blocks are found. The accounting works and the number is saved. Another day, a careful count indicates that there are 30 blocks. This causes considerable consternation until it is realized that a neighbor boy came to visit. He brought his blocks with him, and he left a few at the house. After she has disposed of the extra blocks, she closes the window and does not let the neighbor in. Everything is going along all right until one time she counts and finds only 25 blocks. This is where the situation becomes interesting. There is a toy box in the room. The mother goes to open the toy box, but the boy screams and says she is not allowed to open it. She has a problem. She has 25 visible blocks. She is missing 3. She suspects they are in the box, but she cannot see them. The energy is hidden. Being extremely curious and somewhat ingenious, she invents a scheme. She knows that a single block weighs 3 ounces, so she weighs the box at a time when she sees 28 blocks, and it weighs 16 ounces. The next time she wishes to check, she weighs the box again. She subtracts 16 ounces and divides the result by 3. She discovers a formula. The number of blocks seen plus the weight of the box minus 16 ounces divided by 3 ounces equals a constant. There then appear to be some new deviations in the mother's calculations. Careful study indicates that the dirty water in the bathtub is changing its level. The child is throwing blocks into the water and she cannot see them because the water is so murky. However, she can find out how many blocks are in the water by adding another term to her growing formula. Since she knows the original height of the water and she knows that each block raises the water level by 1/4 of an inch, she can calculate the hidden sum. The new formula becomes the number of blocks seen, plus the weight calculation of the box, plus the height of the water calculation. This entire complex equation equals the constant number 28. In the gradual increase in the complexity of her world, she finds a whole series of terms representing ways of calculating how many blocks are in places where she is not allowed to look. As a result, she finds a complex formula involving a quantity which has to be computed and which always stays the same in her situation. Now we must ask, what is the analogy of this story to the conservation of energy? The most remarkable aspect that must be abstracted from this picture is that there are no blocks. Take away the physical items in our equations, and we find ourselves calculating more or less abstract things. The analogy has several key points. First, when we are calculating the energy, sometimes some of it leaves the system and goes away, or sometimes some comes in. In order to verify the conservation of energy, we must be careful that we have not put any energy in or taken any out. Second, the energy has a large number of different forms, and there is a formula for each one. These are gravitational energy and kinetic energy and heat energy and elastic energy and electrical energy and chemical energy and radiant energy and nuclear energy and mass energy. If we total up the formulas for each of these contributions, it will not change except for energy going in and out. But remember that there are no blocks. We do not know what the mechanism is. We just know that if we take the speed of a car and square it and multiply by the mass and divide by 2, we get a number. And if we take the height of a rock and multiply by the weight, we get another number. And if we measure the temperature of a radiator, we get another number. And when we add all these seemingly unrelated numbers together, the total stays constant. It is an abstract thing in that it does not tell us the mechanism or the reasons for the various formulas. It just works. Conservation of energy can be understood only if we have the formula for all of its forms. Let us start with the simplest one, which is gravitational energy near the surface of the Earth. I wish to derive this formula in a way which has nothing to do with history, but is simply a line of reasoning to give you an illustration of the remarkable fact that a great deal about nature can be extracted from a few facts and close reasoning. Consider weightlifting machines. These are machines which have the property that they lift one weight by lowering another. Let us also make a hypothesis that there is no such thing as perpetual motion with these weightlifting machines. That means if we have lifted and lowered a lot of weights and restored the machine to the original condition, and we find that the net result is to have lifted a weight, then we have a perpetual motion machine because we can use that lifted weight to run something else. We assume this is impossible. If you could build a machine that lifts a heavy weight by dropping a light weight a short distance, and then resets itself without using fuel, you would be incredibly wealthy. But nature is stingy. She does not allow it. Imagine a very simple weightlifting machine, such as a lever or a pulley. This machine lifts weights 3 units strong. We place 3 units on one balance pan and 1 unit on the other. However, in order to get it actually to work, we must lift a little weight off the left pan. On the other hand, we could lift the 1 unit weight by lowering the 3 unit weight if we cheat a little by lifting a little weight off the other pan. Of course, we realize that with any actual lifting machine, we must add a little extra to get it to run. This we disregard temporarily. Ideal machines, although they do not exist, do not require anything extra. A machine that we actually use can be in a sense almost reversible. That is, if it will lift the weight of 3 by lowering a weight of 1, then it will also lift nearly the weight of 1. The same amount by lowering the weight of 3. We imagine that there are 2 classes of machines. Those that are not reversible, which includes all real machines, and those that are reversible, which of course are actually not attainable, no matter how careful we may be in our design of bearings and levers. We suppose, however, that there is such a thing as a reversible machine, which lowers 1 unit of weight by 1 unit of distance, and at the same time lifts a 3 unit weight. Call this reversible machine A. Suppose this particular reversible machine lifts the 3 unit weight a distance x. Then suppose we have another machine called machine B, which is not necessarily reversible, which also lowers a unit weight, a unit distance, but which lifts 3 units a distance y. We can now prove by logic alone that y is not higher than x. That is, it is impossible to build a machine that will lift a weight any higher than it will be lifted by a reversible machine. Let us suppose that the lifting height of the second machine was actually higher than the lifting height of the reversible machine. If this were true, we could take a 1 unit weight and lower it 1 unit of distance using our irreversible machine. This would lift the 3 unit weight up to that higher level. Then we could lower the weight from that higher level down to the level of the reversible machine. In doing so, we would obtain free power because gravity is pulling it down for that extra distance. Then we could use the reversible machine running backwards to lower the 3 unit weight, the remaining distance, and lift the 1 unit weight back to its starting point. The result is that everything is reset to the original position, but we have generated free power during the drop. This is perpetual motion. We assumed this was impossible. Therefore, we deduce logically that the second machine cannot lift higher than the reversible one. This means that of all the machines that can be designed, the reversible machine is the most efficient. We can also see that all reversible machines must lift to exactly the same height. This is a remarkable observation because it permits us to analyze the height to which different machines are going to lift something without looking at the interior mechanism. We know immediately that if someone makes an enormously elaborate series of levers that lift 3 units a certain distance by lowering 1 unit, the result will be predictable. So what is this distance? Suppose we have a reversible machine lifting 3 units by dropping 1 unit. We can prove by logic alone that the distance must be 1/3 of a foot. The generalization is clear. 1 pound falls a certain distance in operating a reversible machine. Then the machine can lift a certain amount of pounds. The rule is that the weight multiplied by the height is constant. We call the sum of the weights times the height's gravitational potential energy. This is the energy which an object has because of its relationship in space relative to the Earth. The formula for gravitational energy, so long as we are not too far from the Earth, is the weight multiplied by the height. It is a very beautiful line of reasoning. The only problem is that perhaps it is not true. After all, nature does not have to go along with our reasoning. Perhaps perpetual motion is in fact possible. However, it turns out experimentally to be true. But this is just the beginning. We have only talked about statics, which are things standing still. What happens when things move? Where does the potential energy go when a pendulum swings down to the bottom? The gravitational energy disappears when it is down at the lowest point. Nevertheless, it will climb up again. The gravitational energy must have gone into another form. Evidently, it is by virtue of its motion that it is able to climb up again. So we have the conversion of gravitational energy into some other form when it reaches the bottom. We call this kinetic energy. Just like with the blocks, we need a formula for it. We need to find where the blocks are hiding when the object is moving. Trust me when I say that the formula for motion is where things start to get really messy. We left off with a nice tidy picture of the universe where we had weights and heights. We established that if you lift the rock, you are storing a number called gravitational potential energy. But the universe refuses to sit still. What happens when you drop the rock? As it falls, it loses height. The gravitational potential energy is vanishing. The number on our balance sheet is dropping towards zero. If the law of conservation of energy is real, and if those indestructible blocks have not simply ceased to exist, they must have gone somewhere. They must be hiding. Look at the rock just before it hits the ground. It has no height left, but it has something else. It has speed. It has motion. If we attach that moving rock to a rope and a pulley system, its motion can pull another weight up. It has the capacity to do work. The energy did not disappear. It shape-shifted. It turned into kinetic energy. Now we need a formula for this. We need to know how many blocks are hidden in a moving object. Recall our arguments about reversible machines. We can see that the motion at the bottom must correspond to a quantity of energy that permits the object to rise back to a certain height. It does not matter how it got that speed. It does not matter whether it fell from a cliff or was shot from a cannon or was pushed by a rocket. Motion is simply motion. When we do the math, we find a specific rule. To find the kinetic energy, you take the weight of the object and multiply it by the square of its velocity and divide by a constant related to gravity. Notice that the velocity is squared. That is critical. If a car goes twice as fast, it does not have twice the energy. It has 4 times the energy. This is why high-speed impacts are so much more violent than low-speed ones. The number of hidden blocks explodes as you go faster. So now we have 2 places to hide our blocks. We can hide them in height, which is potential, and in speed, which is kinetic. Is that the whole story? Is the universe just things going up and down and fast and slow? Of course not. Nature is far more devious than that. Consider a spring. If you pull down on a spring, you are doing work. You are sweating and pulling against the metal. You hold it there. The spring is not moving, so there is no kinetic energy. It has not changed height, so there is no gravitational energy. Yet you know there is energy there. If you let go, it snaps back. It can lift weights. It can smack you in the face. We have to invent a new term called elastic potential energy. This is the energy stored in the tension of the spring. But wait, there is a significant problem with our logic so far. We have made a dangerous assumption that undermines everything we have just established. Throughout this entire explanation regarding reversible machines and swinging pendulums, we have been cheating. We have been assuming that these machines go on forever. We assumed that a pendulum swings back up to exactly the same height it started from, and we assumed the spring bounces for eternity. But you know from experience that this is a lie. If you swing a pendulum, eventually it stops moving. If you bounce a spring, eventually it settles down into stillness. When the pendulum stops, it has no height left, so the gravitational potential energy is zero. It has no speed left, so the kinetic energy is zero. The numbers on our balance sheet have vanished. Did the blocks disappear? Did nature finally break the law? Where did the energy go? This brings us to the most brilliant hiding spot of all, which is heat. Inside the spring and inside the pendulum and inside the air they move through, there are crystals and molecules made of billions of atoms. When things move on a large scale, like a car rolling down a hill or a pendulum swinging through an arc, we try to be very delicate. But nature is messy. There is friction, and there is bumping, and there is resistance. As the large-scale motion slows down, the visible kinetic energy disappears. But invisible kinetic energy appears. The atoms inside the material start to jiggle. They start to wiggle in a random and confused manner. We lose track of the energy on the macroscopic scale, but it is still there. If you put a sensitive thermometer on a spring that has just stopped bouncing, you will find that it is warmer. That warmth is the energy. Heat energy is not a separate entity. It is just kinetic energy that is hidden in the chaos of the crowd. This is a profound realization because it means that what we call heat is just the motion of atoms that are too small to see. The blocks did not vanish. They just got chopped up into dust and scattered among the billions of atoms. But if you could count the motion of every single atom, the total number would still be exactly the same. Once you accept that energy can hide in the jiggling of atoms, you start to see it everywhere. There is electrical energy. This has to do with pushing and pulling electric charges. There is radiant energy. This is light. We know light carries energy because it heats up the pavement and it burns your skin. Light is just a wiggling in the electromagnetic field. There is chemical energy. This is the energy released when gasoline burns or when you digest food. But what is it really? It is just the electrical energy of atoms attracting and repelling each other. It is the same rules, just operating deep inside the chemistry. There is nuclear energy. This is the energy involved with the arrangement of particles inside the nucleus of an atom. We have formulas for it, but honestly, we do not fully understand the fundamental laws of it yet. And finally, there is the monster, the one discovered by Albert Einstein called mass energy. It turns out that an object has energy simply from its sheer existence. Even if it is sitting still at absolute zero temperature with no height and no electric charge, it has energy because it has mass. If you take a positron and an electron and you bring them together, they disappear. They annihilate each other, and out comes radiant energy. You can calculate exactly how much energy appears. The formula is the mass multiplied by the speed of light squared. This means mass and energy are the same thing. Mass is just a very dense way of storing the blocks. So where does this leave us? We have a law called the conservation of energy. That seems to be absolutely true. We check it in steam engines and in stars and in atoms and in galaxies. The number always balances. The blocks are always found, whether they are under the rug or in the toy box or in the jiggling of atoms. But remember what I said at the beginning. We do not know what energy is. We do not understand energy as counting little blobs. It is a mathematical quantity. It is abstract, and it gets stranger. In quantum mechanics, we learned that this conservation law is actually related to time. It turns out that conservation of energy is just the physicist way of saying the laws of physics do not change depending on what time it is. If you do an experiment today and you do it again tomorrow, nature behaves the same way. That symmetry in time is what causes energy to be conserved. Energy is not a substance. It is the shadow cast by the consistency of reality. Before we conclude this journey into the abstract heart of physics, I must issue a serious warning. I have told you repeatedly that energy is conserved. I have told you it is indestructible and eternal. Logic dictates that if something cannot be destroyed, we can never run out of it. So you might ask why we have an energy crisis. You might ask why global superpowers fight wars over oil, or why you must pay a monthly electric bill if the electricity is strictly conserved by the laws of the universe. The answer lies in the difference between the quantity of energy and the quality of energy. While the total amount of energy in the universe is constant, the amount of useful energy is constantly dropping. Think about the ocean. The water in the sea contains a staggering amount of heat energy. The atoms are jiggling with kinetic power. However, you cannot convince those atoms to herd together and push a ship across the Atlantic. The energy is there, but it is disorganized and chaotic. To get work done, you do not just need energy. You need a difference. You need a flow from hot to cold, or from high to low. You need order. When you burn coal to run a steam engine, you are taking organized chemical energy and turning it into heat. You use that heat to do work, but in the process, you scramble the energy. You turn it into low-grade waste heat that dissipates into the atmosphere. The blocks are still there. The number is still conserved, but the blocks are now scattered so widely that you can never gather them up again to do anything useful. This is the tragedy of entropy. Nature does not care about your electric bill. She obeys the law of conservation strictly, but she is a spendthrift. She spends energy in all directions without hesitation. The sun is a giant nuclear furnace in the sky. It liberates massive amounts of energy every single second. It throws this wealth out into the dark void of space. We on Earth are like beggars standing with a tiny cup. We catch only a fraction. 1 part in 2 billion of the output from the sun hits our planet. The rest is lost to the deep cold of the cosmos. Our job as physicists and engineers is not to create energy because that is impossible. Our job is to figure out how to catch those falling blocks before they get hidden under the rug of entropy. We are simply trying to build better cups. Consider where we get our power. We get it from the sun directly through solar panels. We get it from rain, which fills our dams and turns our turbines. But rain is just the sun lifting water into the sky. We get it from coal and oil. But what is coal? It is just ancient sunlight stored in the bodies of dead plants. It is a battery charged millions of years ago. And then there is uranium. This is energy stored in the nucleus of atoms during the violent death of ancient stars. But there is a greater hope on the horizon. If we can figure out how to control thermonuclear reactions, which is the same fire that burns in the sun, we could solve our problems forever. We call this fusion. The fuel for this fire is hydrogen, and hydrogen is found in water. If we can unlock this technology, we could get enough energy from 10 quarts of ordinary water per second to power the entire United States. The blocks are there. They are floating in your bathtub. We just need to be smart enough to find them. So the next time you hear someone use the word energy, I want you to pause. Do not picture a glowing blue fluid pulsing through a wire. Do not picture a lightning bolt. Picture a mischievous child named Dennis hiding his blocks in a room. Picture a mother frantically calculating sums to make sure nothing has been lost. Picture a number that refuses to change no matter how much the universe twists and turns. We do not know what energy is. We cannot hold it in our hands. It is a ghost. It is a shadow. It is a mathematical abstraction. But it is the one thing in this chaotic and confusing universe that we can actually count. And in a world of uncertainty, that constant number is the closest thing we have to absolute truth.